In this video, we're going to talk about what electromagnetic waves and radiation can do when they hit matter. Right. So up here, I've kind of labeled 4 examples, and again, they're all kind of simplified. But you can have an electromagnetic wave, and this black line here is supposed to be like, some kind of matter, and it could just pass right through it, and that's called transmission. And all that means is that that material is transparent to that specific wavelength of light. And different materials will be transparent to different frequencies, different wavelengths. And again, that just depends on the material and the wavelengths involved. Number 2, I have as absorption, and that means that the matter actually absorbs the energy from the electromagnetic wave. And once the energy is absorbed, depending on the amount and what kind of matter it is, it'll kind of do different things with that energy. So some possibilities are the electrons in that matter could jump to higher energy levels, and I'll explain that in the next video. It might start rotating or vibrating, it really depends on the material. Number 3 is reflection, so that's when the wave comes, it hits the surface of something, and then it kind of reflects off, bounces off. And number 4 is scattering. And again, I'll explain that as it's like reflection, so the wave comes in and hits the surface, but instead of being reflected at this one specific angle, it kind of scatters out at a few different angles. And now I want to use that to start talking about color. So transmission, again, is important for like what can visible light go through, like what can we see through, right? What can light go through? Absorption and reflection and scattering become very important in how our eyes perceive objects. So the visible part of the light spectrum is the one narrow band of light that we can actually see. Our eyes can actually pick it up. And the different frequencies or wavelengths of light, our brain kind of associates with different colors. And so this is the kind of the visible spectrum. And you'll see that the high frequencies are purple, then it goes kind of blue, light blue, green, yellow, orange, reddish. And then the acronym I like to use is Roy G. Biv. And that's over here. R for red, O for orange, Y for yellow, G for green, B for blue, V for violet. And you see that's red, orange, yellow, green, blue, violet. And so say I have a shirt, this is my shirt, and I send all of these frequencies at it at once, Roy G. Biv. That is what we perceive as white. That's going to be what we call white. Again, just kind of how our brains work. So we send all of these frequencies together, that's white light, hits the shirt. Let's just say that the shirt absorbs these frequencies, orange, yellow, green, blue, violet. But it reflects red. So that red that's reflected off this shirt is what kind of goes into our eyes. And that's how our eyes register objects, by kind of the light that goes into them. And so we would see this shirt as red, but really what we're seeing is the frequencies of light that shirt happens to reflect. But we would call that shirt red. If we got that same shirt and shined orange, yellow, green, blue, violet light at it, so it's not white light, it does not have red. Remember, it absorbs orange, yellow, green, blue, violet, and it reflects red, but only if red is there to be reflected. And so no red can get reflected off this shirt into our eyes, and when there's kind of no light hitting our eyes, the color we associate with that is black. So we would see this shirt as black if there were no red light to reflect off of it. This can be seen in kind of the eternal question of why is the sky blue? So the sun releases white light, red, orange, yellow, green, blue, violet. But air in our atmosphere scatters that light, and it scatters higher frequencies more readily. So it'll kind of tend to scatter the kind of violet and blue frequencies more. And so when you look at the sun, the purple and violet are scattered out, and when you see it, it's kind of like a white, but kind of like with a yellowish tinge, and that's because it's lost some of those high frequencies. When you look up at the sky, you'll see that scattered light, and your brain will register that as blue because the violet isn't as strongly picked up. And if you're at sunset, the sun will have to go through even more sky, so even more wavelengths will be scattered, some green will be scattered out, and you'll be left with just red, orange, yellow, which we'll see as red. That's why the sky is red at sunset.